Hey, Week North, Mr. Yergler here. We're going to talk about theoretical and percent yield. By this video, you should be pretty comfortable with basic dimensional analysis, be able to calculate basic stoichiometry questions, and now we're kind of taking it a step further. So now we're going to add on percent yield and theoretical yield. All right, let's get started. Let's say you're making sandwiches, and you have 20 pieces of bread, 11 pieces of cheese, and 36 pieces of meat, or ham in this case. And you want to know how many sandwiches you can make. Well, you have enough bread to make 10 sandwiches, right? Because you need 2 slices of bread for each sandwich. According to our recipe here, we only need 1 slice of cheese for our sandwich, and so we have enough cheese to make 11 sandwiches. Our recipe calls for 3 slices of ham, and so we have enough ham to make 12 sandwiches. Using just what we have in terms of cheese, we can make 11 sandwiches. However, in reality, we can't make 11 sandwiches because we'll run out of bread first. Okay, and in this case, our limiting reactant, our limiting reagent, is the bread. Because the bread, even though you have enough cheese to make 11 and enough meat to make 12, the bread limits how much you can make, right? You run out of bread first. So the limiting reagent is the reagent that you run out of first, the one that makes the least amount of product. Let's tie this to more of a chemistry context. Let's say this is our chemical reaction. We have sulfur and fluorine, and we're making sulfur hexafluoride. If we have only 4 moles of sulfur and 2 moles of fluorine, the question is how much product can we make? Notice you're given 2 different amounts of 2 different reactants, right? We actually don't know. This is kind of like the bread and the cheese. You don't know which one's going to run out first until you first figure out how much product can each one make. So our 4 moles of sulfur is enough to produce 4 moles of sulfur hexafluoride. You could also think of this in terms of molecules, right? 4 molecules of sulfur will make 4 molecules of sulfur hexafluoride because they're in a 1-to-1 ratio, right? It's a balanced equation, and there's essentially a 1 here and a 1 here. If we only have 2 moles of fluorine, though, that's not even enough to make a single mole of sulfur hexafluoride. We need 3 of them to make 1 mole of sulfur hexafluoride. So the 2 moles that we have is enough to make like 2/3 of a mole of the product. Okay, so in order to figure out which one's limiting, you got to think about which one runs out first or which one makes the least amount of product, right? Same thing. In this case, the F2 is making the least amount of product, and so it's going to be the limiting reagent, the one that runs out first. We're going to have excess sulfur, like sulfur unreacted, leftover sulfur, so to speak. Let's do this in a situation where we actually have to do a calculation. You're going to often be given grams instead of moles, which makes it a lot more complex. But it's more realistic because we always measure things in labs in grams. We can't measure things directly in moles. So let's say we have 637.2 grams of ammonia, that's the NH3, and it's reacting with 1142 grams of carbon dioxide. So we're given 2 reactants, and so we don't know which one's going to run out first, right? Find the limiter, find the limiting reagent, and the amount of urea produced. So it's asking for the urea. So let's actually use the stoichiometry to calculate how much urea this is actually going to make. Each one of these are going to make separately, assuming we use them all. Ignoring the water, because there's 2 products in this case, and all of our other examples have so far have only had 1 product. We can kind of pick one of the products, and since the question's asking specifically for urea, we're obviously going to pick urea. All right, I'm going to do this on paper so it's a lot easier for me to show and for you to see. Here's our balanced equation, and I like to write the amounts above each reactant and kind of our target compound or target units and substance above, the product that we care about in our particular case. Now, again, we don't know how much this is going to produce, and we don't know how much this is going to produce separately. We don't know which one's going to run out first. And when we get to the end, when one of them runs out, we have excess left over. And so you can't assume that we're going to use, all of this. So we actually have to do these 2 calculations separately. So let's start with the ammonia, the NH3. I'm going to start with my given, 637.2 grams, do my molar mass conversion to moles, 17.03 grams of ammonia to 1 mole. Now I'm in moles of ammonia. I need to get to moles of urea, and then from there I can get to grams of urea. So this is where my mole ratio comes in. 2 moles of ammonia produce 1 mole of urea. So I'm going to do 2 moles of ammonia down here to 1 mole of urea. This is where it's really important to actually write out the substance that you're talking about, because you're switching. They're both moles. And so if you would just write 1 mole over 2 moles, it's really easy to get them switched around because you're not paying attention to which one cancels. One last step into grams, we're going to use the molar mass, which is 60.06 grams. I actually just Googled that. Save yourself a little bit of time when it comes to homework problems. Once you're proficient, you know what molar mass is and how to find it. You can save yourself some time by just Googling molar mass of whatever the compound is, and it'll spit it out for you. Obviously, you need to know how to do it, when you're taking a test or something. So we have enough ammonia to produce 1124 grams, but we don't know if we're actually going to produce 1124 grams because we don't know if we're going to run out of carbon dioxide first. So we need to figure out how much that can produce. So I'm going to take my given amount of carbon dioxide, convert it to moles. The molar mass is 44.01 grams per mole for carbon dioxide. Then my mole ratio here is 1 to 1, and I'm going to go ahead and write it out. 1 mole of CO2 to 1 mole of urea, and then it's the same molar mass conversion. This comes out to 1555 grams. Now, we have two amounts of the same product, right? We have to be producing this amount because we have enough carbon dioxide to produce 1500 grams, but we don't have enough ammonia to produce 1500 grams. We only have enough ammonia to produce 1100 grams. And so this is the true amount that we would actually make. So you'd actually have leftover, we have excess carbon dioxide, and we can calculate how much excess we have. So my answer for how much would I actually produce would be the 1124. So in question 2, how much excess is left over after the reaction goes to completion? So we figured out that carbon dioxide is the excess reagent, but we didn't figure out how much is left over, how much is unreacted after we're done. There's a couple different ways to do this. We can figure out based on how much this produces and how much this produces, which we've already calculated. We could subtract those two. That tells us the amount of urea that could have been produced if we would have reacted all of our carbon dioxide. So taking the subtraction of that and then back calculating that from urea, grams of urea, back to grams of carbon dioxide. That's one way to do it. Another way to do it is to say that we know that we're using all of our 637.2 grams of ammonia because this is limiting, it's running out first before we run out of carbon dioxide. And so we know that we're going to actually produce 1124 grams and use up all of the 637.2 grams. So what we could do is we could say, okay, let's figure out how much carbon dioxide is needed to use up all of that 637 grams of ammonia. From there, it's obviously going to be less than 1142. We would take the subtraction, and that would be what's left over. A third way to do it would be to take the amount that we're going to produce and calculate back how much carbon dioxide did that use up, and it's going to be less than 1142, and then we could subtract that. So it's all just a difference in when you subtract and when you don't, and what product or reagent you're using to calculate to CO2. I'm going to go ahead and do it the way that I think it was the second way that I said. Based on how much we're using here, how much did that require to be used up of carbon dioxide? So assuming using all of my ammonia, instead of running to urea, I'm now going to calculate how much carbon dioxide does that require. So same molar mass conversions, grams of ammonia into moles of ammonia. Instead of doing my mole ratio from moles of ammonia to moles of urea, now I need to go to moles of carbon dioxide, which is actually still the same ratio. It's 1 to 2. Now that I'm in moles of carbon dioxide, I can go into grams of carbon dioxide. So according to this, I would have used up 823.3 grams of carbon dioxide. I have 1142, and so the difference between those is what I have left over. Alright, let's get a few definitions down. The theoretical yield is what we just calculated. It's how much product will be synthesized in ideal conditions. Assuming you don't lose any in the lab, assuming you're transferring every last molecule from one container to the next, how much in ideal conditions you should theoretically produce, right? It's basically just the amount of a product produced according to these stoichiometric calculations, which is what we've just done. The actual yield is how much you actually produce when you physically do a lab, okay? And this will often be given to you in a problem. It'll say something like, it'll give you an equation and then say something like 100 grams was actually produced. What's the percent yield, right? The percent yield would be your actual, what you physically collected in the lab versus what your calculations say you should collect. Let's look at an example. Going back to the same problem with the same numbers, Let's say we carry out this reaction and only 983.5 grams of urea is actually collected. What's the percent yield? Going back to our calculations, we know that we should theoretically produce 1124 grams of urea. However, the problem is telling us that we actually only produced 983 grams. So the percent yield is just the percentage of those two numbers. Real simple calculation. What the problem says we actually collected, 983.5 grams, over what we theoretically should have collected, 1124, times 100 to make it into a percentage, 87.5% is our percent yield of our lab, or of our reaction. So that's theoretical yield and percent yield. We've just did essentially one practice problem. We'll get more practice problems in class to get proficient at it and be able to use it in new situations. All right, this is Mr. Yergler signing off.